Do you remember my last lecture? It was like way back like 6 days ago. I said at the beginning of the lecture that I was going to cover a lot of stuff, and I think a few different times during the lecture I said that in the next lecture I'm going to talk about locally compact groups. But then I watched all of Anish's lectures, and also I saw some of Vaughn's review sessions, and I realized that that might have already been covered. And I don't want to spend a lot of time talking about locally compact groups and harm measure and things like that. And so I'm going to go ahead and I'm going to skip that one part of what I said I would talk about. And instead I'm going to move forward and I'm going to talk about the Furstenberg orbit closure theorem. So today's talk is going to be a lot more about dynamics than the previous one was. In the previous one I was trying to give you an intro to Diophantine approximation, in particular so that you could try to have some background and some way to understand some of the things that the speakers were going to talk about. Now I want to actually just talk about something which is going to seem a little bit different. It's just a topic from Dynamical Systems, Furstenberg orbit closure theorem. And maybe to motivate this at the beginning, I'll say something which is hopefully close to obvious to a lot of you. First of all, the multiplicative semigroup of natural numbers acts on the circle R mod z by endomorphisms, right? By the rule, what does an integer n do to a number alpha? Well, it sends it to n alpha mod 1. Okay. Now, one of the exercises on the sheet there is, and this is actually pretty easy. Don't try to do this in any kind of like super sophisticated way. The idea is to try to give an easy proof. It's easy to show. So whoever can prove this, whoever can give the simplest proof of this is the winner. That if I take the orbit of any point under the action of the full semigroup and then I take the closure, what am I going to get? Well, there's only two possibilities, depending on whether or not the point alpha was a rational number, right? If alpha is irrational, then I'm going to get everything. So my orbit is going to be dense. And if alpha is rational, well, I'll just say this way, then I'm going to get a finite orbit. Okay? Right? Everybody believes that. Everybody, I'm sure, believes that. But you still have to try to prove it. You have to try to give the simplest possible proof that you can think of. So if you find a really simple proof, come and tell me, because I'd like to see who gets the simplest. What can you say? Now, this is the general question that I'm going to try to address now. What can you say about orbits for actions of subsemigroups of the natural numbers? What about orbits for actions of subsemigroups? Well, this question turns out to have a really nice, clean answer. And in order to understand the answer, let me first tell you about one extreme. One extreme is if you have I'm talking about multiplicative semigroups, by the way. So one extreme is if I have a semigroup which is generated by just one number, like the times 2 map on the unit circle. And so let me talk about that extreme first. So here's an example. In this example, let's suppose that my semigroup sigma is generated by just one integer bigger than 1. So let's suppose that it's something of the form a to the k, where k is bigger than or equal to 1. And here I'm assuming that a is bigger than or equal to 2. Okay. Well, what can I say about the collection of all possible orbits of numbers under the action of this semigroup? You guys should have some feeling about it already.
So a is an integer?
A is an integer, yes. Okay. What can you say about the collection of all possible orbits. Do I still have a dichotomy like this, that every orbit is either dense or it's finite? No, why not? Can you just give me a simple explanation for why not? If you've looked at some of Vaughn's exercises, they might have given you a little bit of a clue. I'm also going to actually connect this to what Valerie's talking about, because let's just think about it this way. I can't hear you.
Could it be going into an infinite orbit but in a Cantor set-like way with these big gaps?
Yeah, that's one way that you can do it. Have you guys tried to construct have you guys tried this exercise on Vaughn and Will's exercise sheet where it says to construct infinitely many different ergodic measures for the times 2 map or something like that? Or maybe it's times a map.
But it's the isomorphic to anything else that you want.
Well, so how did you do that for those of you who did it?
Markup measures?
You can just construct a Bernoulli measure, right, where you just chop up the measure at each stage. You distribute it among you divide your interval into a distinct pieces, all of the same size, and you divide the measure in some way among them, and then you continue that process, so you form this sort of Bernoulli measure. And in the end, you end up getting a measure which is times A invariant, which is ergodic, but which is not Lebesgue measure. And there's uncountably many different ways of doing that. So that's one way to see that you can. Oh, but that doesn't say anything about orbit closure, right? That doesn't say anything about the topological property of orbit closure. So to see why you can get uncountably many different orbit closures, what you can do is you can think about this. Let's think about this in terms of Valerie's notation. Let's choose a subshift of the alphabet from 0 up to a minus 1. Okay? So let's let this be a proper subshift. Now there's some stuff here that I'm not going to prove. But here's the point. If I so what letter did you use for the shift map? Did you use sigma for the shift map? You use little s for the shift map? Oh, big S for the so I already messed this up then. Sorry. I'm going to use little sigma for the shift map, okay? Yeah?
No, I use sigma.
Oh, you use sigma. Okay, good. Yes. So the point is this, that if I consider the left shift, the dynamical system given by left shift on this shift space is conjugate to something. It's conjugate to, how should I explain this? It's topologically conjugate to a multiplication by a map on the unit circle. Okay? It's conjugate to multiplication by a. Mod 1. On R mod C. And I guess I should say I didn't put enough information into this to be able to say this in a really clean way. Restricted to the identification of S. With the subset of 0, 1 given by the map that takes a word, W equals W1, W2, ... and it identifies it with the base A expansion of a number in the unit interval. Okay? Do you see what I'm saying? So in order to see that there's infinitely many different orbit closures, what you can do is you can just start with a subshift, a proper subshift on the alphabet from 0 up to a minus 1. And you can just identify every word in that subshift with the base A expansion, right here on the end base A, with its base A expansion in the unit interval. Then the shift map is conjugate to just multiplication by A mod 1 in the unit interval. And so you have well, the thing that I didn't show is that in this way you get uncountably many different orbits. Okay? But if you can believe me that that's true, then already you can see that if you're just considering a semigroup generated by one element, you have a very rich collection of orbits. Okay? Uncountably many. Now, what the Furstenberg orbit closure theorem says is that if you have a semigroup, a subsemigroup of the natural numbers which is not generated by just one element, then again you're going to be back in this case where you have a dichotomy, where either every orbit is closed or you have or is finite. Okay? I'm going to write that on the board in just a minute. So let me now make a definition. Definition here. Semigroups of n generated by one element. Like in the example that I gave, are called lacunary. Okay? And one of the exercises that I put on the sheet for you, I hope, is this. So a semigroup sigma of the natural numbers is non-lacunary if and only if and only if it contains two multiplicatively independent positive integers. Okay? Multiplicatively independent positive integers. Okay? By the way, I really mean integers bigger than 1. I don't just mean positive integers here. Okay. So what is multiplicatively independent? Multiplicatively independent, I'll just tell you what that means. So A and B are multiplicatively independent. A and B bigger than or equal to 2 are multiplicatively independent if the logarithms of the numbers log A and log B are q-linearly independent. Okay? Q-linearly independent. This is a fairly easy exercise. I wouldn't say it's not as easy as the first exercise that I just told you about. It does actually take a little bit of thought, a small amount of thought. I think you should sit down and try and prove this. If you have a subsemigroup of the natural numbers and it's not generated by one element, then it contains two multiplicatively independent integers. So an example of a non-lacunary semigroup would be, I'll give you an example. So an example of a non-lacunary semigroup would be the semigroup generated by, OK, I'm sorry to be boring here, but I'm going to put here 2 to the k and 3 to the l, OK, where k and l are bigger than or equal to 1. OK?
Why is that boring?
I could have put like 2 to the k times 6 to the l or something like that. Maybe that'd be. There's nothing that's not really that boring. That's kind of what the exercise is saying. You can always find two multiplicatively independent integers in there. Okay. Okay. So let me tell you what the theorem says now. So the Furstenberg orbit closure theorem, which is proved in the 1960s, it says if I have a non-lacunary subsemigroup of the natural numbers, then when I consider the orbit closure of a number, there's only two possible things that can happen. If the number alpha is irrational, then I'm going to, again, have an orbit which is dense. So when I take the closure, I'm going to have the whole circle. Otherwise, I'm going to have an orbit which is finite. OK? And so that, at the beginning of the talk when I was just saying we're going to look at the collection of all orbit closures for all possible sub-semigroups of the natural numbers, that could have ended up being a really hard problem that we'd end up spending 4 lectures on. But it turns out that it's only going to take 1 lecture, because either you're a sub-semigroup generated by 1 element, which we sort of understand in terms of shift spaces, like what Valerie's talking about, or you're a sub-semigroup generated by which contains at least 2 multiplicatively independent integers, in which case you have this dichotomy again. That's a pretty cool result, right? So I'm going to prove it. That's the goal of today's lecture at a minimum. Now that I've said that, I guess I better get going. So first of all, I need a lemma. This is kind of an important lemma. And in the lemma here, I'm going to suppose that I have a non-lacunary sub-semigroup of the natural numbers. I'm going to write it in order. It's non-lacunary. Then, you guys can tell me if you've seen this problem before. Then if I take the limit of ni plus 1 over ni, as I tends to infinity, I get 1. OK? Who's seen this before? I wrote this on the board when I first got hired here to see if anybody would put a solution up out in the hallway. So this is pretty cool. In the exercises, I asked you a question like this as well. I asked you to prove something which is a little bit of a refinement of this. So let me show you how do you prove the statement that I've written on the board here. Well, so here's the proof. Without loss of generality, let's just reduce to the case where sigma is just the semigroup generated by 2 elements. Okay? I hope that you see that we can do that without loss of generality. So without loss of generality, let's just assume that we're in the case where sigma is actually generated by A and B, and A and B are multiplicatively independent. A and B multiplicatively independent. OK? I know that my sub-semigroup contains 2 multiplicatively independent integers, and I know it's a semigroup, so products of elements stay inside of there. And so if I can just show that what I'm trying to show is true for semigroups that look like this, that are generated by just 2 multiplicatively independent elements, putting in all the extra elements into the semigroup, if there are any, it's not going to change the fact that the limit of the ratios of consecutive elements tends to 1. It's just going to thicken up the set. So let's try and do this. Now, let's write the ith integer, ni, as a to the ki times b to the li. OK? And I'm just trying to introduce a little bit of notation here. Let's write ki prime for the difference between the I plus first exponent and the ith exponent. And let's write li prime for the difference between the li plus 1 and the li. OK. Well, then, when I look at ni plus 1 divided by ni, I get exactly a to the power ki prime times b to the power li prime. Agreed? That's just from the definitions. And just to be clear, what we're trying to show, what we want to show, is that for every epsilon bigger than 0, there exists a number I naught such that for all i's bigger than or equal to I naught, the ratio between ni plus 1 and ni is bigger than or equal to 1. Well, that's a given. That's given to us. And is less than or equal to 1 plus epsilon. OK? OK, now, what I want to do now is I want to take the logarithm in each of these 2 inequalities. So this is equivalent to showing that, well, what do I get when I take the logarithm? I'm going to get ki prime times log a plus li prime times log b bigger than or equal to 0 and less than or equal to log of 1 plus epsilon. Now, by a simple power series approximation for the function on the right-hand side, log of 1 plus epsilon is bounded above by some constant times epsilon, universal constant times epsilon, as long as, let's say, as long as epsilon is less than a half, which it is, because it's tending to 0. And so by replacing epsilon with a new number, I'll call it epsilon prime, I can absorb it. I can absorb that constant into the approximation, right? So I'm trying to show now that for any epsilon prime bigger than 0, something like this holds. It's equivalent to what I'm trying to show. Now, where is this going? I don't want to tell you exactly where it's going because I don't want to ruin the exercise. But I'm not going to get that on me. So, OK. Now, let me just divide both sides of both inequalities here by log b, and let me also divide by ki prime. And so what I'm trying to show is equivalent to the statement that I can well, let me not repeat all the quantifiers because there's no need for that kind of ceremony here. I'll just write down what I'm trying to show on the board here. I'm trying to show that I can choose all my, that given epsilon prime, I can choose all my parameters so that this is true, right? For all I sufficiently large. Say again? I'm sorry, I couldn't hear you. Oh, yeah, yeah. Can I just call it just epsilon prime? Is that all right? Epsilon double prime or something? OK, I'll put the log b in there. Now you found out, you know how there's these problems that like you know you can do and you just don't want to do it because you. OK, you're right. I need to not be lazy. That's what my mom told me too. OK, here's the idea. Now I'm going to claim something, and I could tell you why this is true in one sentence, but I don't want to because I don't want to ruin the fun. I claim that I can choose integers p and q. I can choose p and q. Just give me a second here. Bigger than 0, yes, such that the distance between log a over log b and p over q is less than or equal to epsilon prime divided by ki prime times log b. Okay? So I'm claiming that I can that no matter what epsilon prime you pick, I can always find, oh, this needs to be a q. This needs to be a q on the right-hand side here. Okay? I'm claiming that no matter what epsilon prime you choose, I can always find a p over q for which this is true. Believe me or not. Why? This is where you're using the fact that log a and log b are q linearly independent. Okay? And I'm not going to tell you exactly why this is true, but I bet if you think harder, you'll be able to figure it out.
Can you repeat the statement, please?
This statement?
No, what is true?
The
thing that you said, is this true?
I said, is this inequality? Is it true that you can always find p and q bigger than 0 with the property that the difference between log a over log b, this quantity, log a over log b minus p over q is bigger than or equal to 0 and is less than or equal to epsilon prime over q log b? Okay? Say it again?
Given a and b.
A and b?
Given a, like we're handed a.
Oh, a and b are fixed from the beginning. Okay? So the fact that this number is an irrational number, log a over log b is an irrational number, tells you that no matter what epsilon prime you choose, you can always find a p over q so that this is true. Now notice that this is also a one-sided approximation. Now does anybody observe that you could actually do a little bit better here? You could. So that's something to think about. Okay? I could actually put something closer to q squared on the right-hand side. But you need to think about why that's true if you want to try and figure out that exercise. Okay? But as long as you believe me that this is true, and I haven't told you exactly the reason why, but it is true, then all I need to do is I've got my P and Q that satisfy this inequality now, and now I want to assume that I naught, let's say, is large enough. Let's just say that I'm just going to say I. Let's assume that I is large enough such that the max of Ki and Li is bigger than or equal to the max of P and Q. Okay? You can do this always because these ni's are tending to infinity. So one of the exponents has got to be big. They can't both be bounded, otherwise your sequence would be bounded. Okay? Now there's two cases we can break the remainder here into two cases. So it's kind of cool how there's like a little bit of Diophantine approximation hidden in the background here, right? If you want to come through and try and improve Furstenberg's theorem, you have to think about this inequality, and that leads you very naturally to the theory of linear forms and logarithms, which is a really difficult subject in Diophantine approximation. It's what Baker got the Fields Medal for. Okay, so under this assumption that the max of Ki and Li is bigger than or equal to, maybe I should just make it bigger. No, it's OK, bigger than or equal to. Is bigger than or equal to the max of P and Q. What I want to do now is I want to divide it into two cases. So there's two cases to finish the proof here. Case number one. If I get to an Ni where Ki is bigger than Li, then I know that the number Ki minus Q is bigger than 0, bigger than or equal to 0. And I also know that the number Li plus P is bigger than or equal to 0. OK? Case number two. If Ki is I'll make the first case if Ki is bigger than or equal to Li, okay, to cover that case. Case number two, if Ki is less than Li, then I can take K to be K1 plus Q1, and I know that that's bigger than Ki plus Q. I don't know where this 1 came from. Forget about the 1. And I know that that's bigger than 0. It's a sum of two positive things, so it better be bigger than 0. I can take L to be Li minus P, and I know that that's bigger than or equal to 0. Okay? Let me tell you what I'm trying to do. Now, I need to finish the proof, but I'm out of space on the board. So can you see the top part of the board right here? Yes, I believe so. I think this is enough space to finish the proof. Yes, it is. So this is going to finish the proof of the lemma right here. So now the idea is that I want to consider the number a to the k times b to the l divided by ni. What can I say about this number? Well, but if you trace backwards through the inequality, I'm using this k and l as substitutes for k prime and l prime. Okay? In fact, one of them has to be minus k prime, and one of them has to be either k has to be minus k prime or l has to be minus l prime, because I have a minus sign right here, but I have a plus sign right there. That's the reason why I had to divide this stupid thing into two cases at the end. It's an annoyance. The point is that I can always choose these numbers so that, tracing back through the steps, so that the ratio between a to the k, b to the l over ni is bigger than or equal to 1 and is less than or equal to 1 plus epsilon. Now, the reason why I didn't just write take k prime to be this and l prime to be this, the reason why I didn't just write that in the end, or take ki, actually what I should be saying here, let me back up a second here. Back up 3 sentences. Here's what I should have said a second ago. K is really supposed to be like ki plus 1. And L is supposed to be like Li plus 1. I said the primes, but that's not right. Okay? So K is playing the role of Ki plus 1, and L is playing the role of Li plus 1. Now, the thing is that I don't really know that these are going to be the next exponents that you're going to see. That's why I didn't put the exponents on there. But what I do know is that when I take a to the k times b to the l, which is genuinely an element of my semigroup since both of these exponents are non-negative, when I take this number and I divide it by ni, I get something which is, by tracing backwards to the inequality, which is bigger than or equal to 1 and less than or equal to 1 plus epsilon. Okay? And so in particular, even though this may not be the next guy that I saw, it's since the ratio between these two guys already satisfies the inequalities that I want, I know that the ratio between the ni plus 1 and the ni also has to satisfy the inequalities that I want, and I'm done. Okay? So that's the proof of the lemma. Now let's talk about the proof of the theorem. Did you guys have questions about that? I know it's a the last step is a technicality. Okay. The last step is a technicality. When you get to this part in the proof, you're trying to say I can choose the differences between the exponents so that they give me a good rational approximation to my number. One of the differences has got to be negative, by the way, because you've got to be able to put a minus sign right there. Okay. Now, how do you do that? Well, you want one of the exponents to be negative, so which way you balance it out depends on which one of the exponents is bigger. Okay? So this is sort of a technicality, but the idea is that as long as these exponents are big enough so that you have enough room to subtract p or q from one of them and still say positive, as long as the exponents are big enough, then you just run through this last case-by-case step and you're done. Okay? Okay. Now, next. I'm going to keep the lemma on the board. I'm going to keep the statement of the theorem on the board. And I'm going to explain now the proof of the theorem. It's a beautiful theorem. By the way, the proof that I'm giving, it is essentially in so the first proof that I learned was from Furstenberg's paper. I think it's worth it to learn that proof. The proof that I'm giving right now is a proof which is sort of extracted from Furstenberg's theorem by Boucher-Nitzen. And basically what it is it's showing exactly what you need in order to prove the statement of the theorem as I've written it here without developing too much dynamical machinery in the background. So Furstenberg's thing is kind of gives you a more general picture of what's going on. But this is just sort of a direct proof of the orbit closure theorem. Now, proof of Furstenberg's theorem. Believe me, believe the lemma now. Even if you didn't completely understand the proof, just believe the lemma. It's a good lemma. Now, let's do this. The part of Furstenberg's theorem is easy. If alpha is rational, then the orbit is finite. So let's not do that part of it, okay? Let's not even put it as an exercise because it's obvious. So the part that's not easy is this. Let's assume that alpha is not rational. And let's also assume without loss of generality, just like we did just a second ago, let's assume that our semigroup is just a semigroup generated by two elements. If it's bigger than that, you can always just throw away stuff and extract the sub-semigroup generated by two elements. If you prove that the orbits are closed when you act by that sub-semigroup, then they're definitely closed when you act by the full thing. So without loss of generality, let's just assume that we're dealing with a case where our semigroup is generated by a to the k and b to the l. I think before I put k and l bigger than or equal to 1, let's put k and l bigger than or equal to 0 because of the inequality that I used over here. Just stupid. Okay? So a and b here, a and b are multiplicatively independent. Now, what do I want to do? I want to develop a little bit of notation. So I want to let x naught be the orbit closure of my irrational point under the action of this two-parameter semigroup. Okay? And I want to make a couple of initial observations here. So number one, this is going to sound totally stupid because I put the bar on top of that. But my first observation is that x naught is closed. Okay, there's going to be an inductive argument in a second, and you're going to want to verify this at every step of the argument.
I'm sorry. I mean, seems like it's rubbing in what you just said about the bar business, but I thought that by definition that was the closure of the bar.
It is.
So then why? Okay, fair enough. Right. mindset.
So what I'm setting myself up for an inductive argument where I define a set x1, x2, and then I define a set xi, and each set xi is closed and infinite and does something, and it's invariant under the action of the semigroup. Okay? So you're right. It's totally obvious. It's like it's a repetition. So it's closed. It's sigma invariant. Okay? And it's infinite. It's infinite because alpha is irrational. And it's important that it's infinite. Okay? Now, I'm going to divide the proof into cases. And there's really two cases, but I'm going to split case 1 into two parts. So this is case 1a. Case 1a. If the set x0 contains a rational number. I forgot that I wrote it this way. P over q. It's not the same P over q as from the proof of the lemma, by the way. If it contains a rational number P over q such that there exists a sigma in the semigroup with q dividing sigma. Okay? Actually, this is a completely wordy way of saying if the closure of the orbit contains 0. Okay, this is what I probably should have written. But no, I'd rather write it this way, because then case 1b is the case when it contains a rational number where the denominator doesn't satisfy this condition. Okay? So if that's the case, then what I can say is that 0 is in the closure of the orbit. Of course, the orbit itself before you close it is a bunch of irrational numbers. So 0 is not in the orbit before you close it. So it means that 0 is an accumulation point or a limit point of the orbit. Okay? So then 0 is a limit point. Limit point of x0. And the fact that 0 is, OK, so now let's use that. Let's use that fact together with our lemma. Let epsilon be some number bigger than 0. You can be your favorite epsilon, but you have to have a sequence of favorite epsilons tending to 0 in the end. And choose a number j large enough such that the ratio between ni plus 1 over ni is less than or equal to 1 plus epsilon for all I bigger than or equal to j. Okay? That's by the lemma. By the lemma, we know we can do that. If we go out far enough, we're going to have ratios as close to 1 as we like. Okay? Now, the fact that 0 is an accumulation point, let's write down what that means. Is this actually board down here as well? Okay. Okay. There exists. The fact that 0 is an accumulation point means that I can find a point, little x, in my set x0 with the absolute value of x. I guess I should put distance to the nearest integer here. I'll put distance to the nearest integer. Distance to the nearest integer. Bigger than 0, that's kind of clear. Less than or equal to epsilon over nj. Okay? I don't want to actually pick the point 0. That's the reason why I put the left-hand inequality. Okay. Let's just suppose without loss of generality that my point x is a little bit to the right of 0. If it's to the left of 0, it's the same. Same argument. So suppose, without loss of generality, that my point x is actually mod 1 is bigger than 0 and is less than epsilon divided by nj. Okay? Well, less than or equal to. Then, what can I say about nj times x? All right, this is all just really easy to see. Maybe I can draw you a picture. Maybe that's an easy way to do this. Okay? Well, nj times x then is from 0 to epsilon, right? And what do I get when I now consider the difference between nj plus 1 times x and nj of x? Well, this quantity is equal to nj times nj, I guess I'll put the x outside as well, njx times nj plus 1 over nj minus 1. And this quantity is bounded above by epsilon. And so this is less than nj, I'll put less than or equal to njx times epsilon. Now, by the way, everywhere I'm working mod 1. So I hope that that's clear. I really mean distance to the nearest integer of njx times epsilon. Okay. Now, I don't know what this number njx mod 1 is, but I know that it's less than 1. And the fractional part of njx is less than 1. So whatever this is, whatever this number is, I know that this is less than or equal to epsilon. Okay. And so what does that tell you? That tells you that when you go from njx to, well, first of all, let me draw here epsilon, and let me put njx in there. It's somewhere inside of there. It's somewhere inside the interval from 0 to epsilon on the circle. When you go from njx to nj plus 1 x, you get another point, which I'll put it right here, nj plus 1 times x. And the distance between these 2 points is less than or equal to epsilon. Okay? I didn't put 2 epsilon there. That's what I was going to do at first, but that's going to mess it up if I do it. Now, when you go to nj plus 2x, you get another point by exactly the same argument. All I used in this argument is the fact that I haven't crossed the finish line yet. The finish line is over here at 1. Once you cross the finish line, you'll break the final inequality here. But before you cross the finish line, each time you take a step, the step goes at most epsilon. And so what you end up getting in the end is you end up getting an epsilon dense set inside the unit interval. The distance between any 2 points here is epsilon. So without writing a ton of symbols and stuff on the board, do you understand the argument? Can you see what's going on here? Each time you take a step from nj to nj plus 1 to nj plus 2, you move by at most epsilon on the unit interval. And that continues until you cross the finish line, and at some point you lose control. Okay? Now, so the conclusion here, the conclusion of this picture is that the set x naught is epsilon dense. Epsilon's arbitrary, and so the conclusion here is that x naught is all of the circle, all of R mod z. And that's the end of case 1. Do you understand the proof of case 1? Actually, this idea in cases 1b and case 2, they both use this idea. The idea is that you can get very close to a fixed point, and then, because there's 2 things going on here. Number 1, because you're working in a sub-semigroup, when you take a point in the orbit and you multiply it by an element of your semigroup, you stay inside the semigroup, so you get a new point in your orbit. And number 2, because your semigroup is non-lacunary, you know that the ratios of consecutive elements are tending to 1. So you know that if you go out far enough, you can make sure that that little step that you take, since you're very close to a fixed point, is very small. And you can get an epsilon dense set on the interval. So case 1b, it's also the case where x naught contains a rational point, but one whose denominator doesn't satisfy that condition. In this case, it's also pretty easy. So case 1b. I'm not going to give you all of the details of this because it's essentially the same argument, but I'll just tell you how to set it up. If x naught contains a rational point, p over q, such that for every sigma in sigma, q does not divide sigma. Okay? Well, now, in this case, by multiplying by, so you know the denominator may have, let's suppose that your semigroup, for example, is 2 to the a, 3 to the b. In case 1b here, your denominator may have some power, the prime factorization may have a power of 2 and a power of 3 in there. But once you clear those out, you're left with a denominator which is co-prime to everything in your semigroup. Okay? So in this case, without loss of generality, we can assume, that the GCD, I'm just writing parentheses here for the GCD, the GCD of q and sigma is equal to 1 for all sigma and sigma. Right? By replacing our number p over q by an appropriate fraction, we can assume that we've chosen one so that the denominator is co-prime to everything in our semigroup. Now, and by the way, I can also assume here that q is bigger than 1. Okay? It doesn't. If q is 1, then you're back in the case of case 1.
sorry, can you say one more time how you make that replacement? I mean, why is this general? Or why is this without loss of generality?
Okay, so if there were a way to multiply my fraction by an element of the, okay, so how do I say that? You write out the prime factorization of the denominator. If all of the primes which are in the prime factorization of the denominator occur as factors of elements of elements in your semigroup, then you can clear the denominator. So you're back in case 1. So case 1b is really the case when there's a prime in there which doesn't occur in the prime factorization of any of the elements in your semigroup. And in that case, you just multiply by something in your semigroup to cancel out all the primes that do occur in your semigroup, and what you're left with is something which is co-prime to everything in your semigroup. Okay. So in this case, in this case, what I can do now is I can replace a by a to the u, let's say. I'll call it a prime. A prime equals a to the u. And b by b prime equals b to the v. So that a to the u times p over q is equal to p over q mod 1 and b to the v times p over q is equal to p over q mod 1. Okay? Do you see why that's true? You just pick a power. Because a and b are both co-prime to q, you can find a power which is 1 mod q. That's all I'm saying. Okay? So you replace your semigroup by a semigroup generated by elements which are 1 modulo the denominator. And now you play exactly the same game as we played in case 1a, because now that fraction is a fixed point for your map. So you've picked an accumulation point which is very close, and then you go out far enough in your sequence so that you know the ratios are very close to 1, and you just step it out to find an epsilon dense subset, exactly in the same way as before. Okay? So dot, 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 proceed as before. Proceed as before to get that x naught is everything. Okay? Done. Case 2. No way. No way. That's already 50 minutes? You're right. That is really hard to gauge. Okay, I think I can do it. It's going to be tough. Case 2. We already dealt with the case where an x naught contains a rational point. Done. So now we're in the case where an x naught doesn't contain a rational point. Okay. Okay, so here's the idea. Let's choose epsilon bigger than 0. And let's choose an integer with q, well, let me say it this way, 1 over q less than epsilon. OK? And oh, by the way, let's just also go ahead and choose q so that it's co-prime to a and b. So GCD of q and a equals GCD of q and b equals 1. OK? Now, without loss of generality, by the same argument as we did before, by replacing a by a suitable power and by replacing b by a suitable power if necessary, we can assume that a and b are both 1 mod q. OK? A equals b equals 1 mod q. So this is as before, by replacing a and b by suitable powers if necessary. OK? Now, what I want to do, this is the inductive part of the argument that I hinted at before. I want to define a new set, x1. x1 is going to be the set of points inside of x0 with the property that x plus 1 over q is also in x0. And I want to make a few observations about this set. And this time it's not going to be as obvious what I'm saying is true, because there's no bar on there. Okay. So observation number 1 is I'm gonna say that x1 is closed. And actually, this observation is actually fairly clear from the fact that x0 is closed. Okay. So let me go ahead and write that as an implication, because that is actually pretty easy to see. So observation number 1, x0 is closed implies that x1 is closed. Okay. Is that okay? Observation number 2. The fact that x0 is sigma invariant implies that x1 is also sigma invariant. Okay? And here's where I'm using the fact that A and B are both 1 mod q. Okay? Step number 3. Or observation number 3, I should say. x1 is infinite. Actually, so let me say something even weaker at first. x1 is non-empty. And the fact that x1 is non-empty implies that x1 is infinite. Okay? Now, here's where I'm using the fact that x0 doesn't contain the rational point. Otherwise, right, because anything that's in x1 has to come from x0. There's no rational points in x0, so if anything survives the process of actually getting into x0, into x1 I mean, then because x1 is sigma invariant, it's got infinitely many points. It has the whole orbit of the point inside of there. Okay? So here's where I'm using, just to repeat, number 2 is where I'm using the fact that A and B are both co-prime, that A and B are both 1 mod q. Because I want to be able to say that if I have a point x inside my set when I multiply by an element, that if I have a point little x inside of x1, it means that x plus 1 over q is also in x0. If I multiply by an element of my semigroup, I have another point inside of x0. And over here, I had a point that started in x0. When I multiply by my element sigma, I get sigma x plus 1 over q. So I'm using the fact that it's 1 mod q right here. And I know that that's also an element of x0 because my original guy was. So here's where I'm using the 1 mod q assumption. Here's where I'm using the assumption that x0 doesn't contain a rational point. Now, I actually didn't tell you why this is true, and this is the non-trivial part of the three of the observations here. I'm going to explain it right now. How do you know that x1 is non-empty? Now we're going to use the same argument that we just used a second ago, where we take a sigma invariant set which has 0 as an accumulation point, and then we thicken it up to the whole set. But now we're going to use it on the difference set of x0. Okay? So check this out. This is actually a pretty cool argument. To see why 3 is true, to see why x1 is non-empty, let's consider the difference set of x0. I'm going to need to give it a name. I'm going to call it delta. Let's call delta the difference set of x0. This is x0 minus x0. The collection of all pairwise differences of the thing. What can I say about this difference set? This difference set is an infinite subset of the torus. Okay? Actually, I should say this way. x0 is an infinite subset of the torus, so it has an accumulation point. So the difference set has 0 as an accumulation point. Okay? So consider this. x0 is infinite. The fact that x0 is infinite implies that 0 is an accumulation point. 0 is an accumulation point. Of course, 0 is in D. 0 is an accumulation point of D. delta. Now also, the fact that x naught is sigma invariant, x naught sigma invariant, implies that the set delta is sigma invariant. Now, who knows what the conclusion of this is? It's the same conclusion as the conclusion we use in case 1a. We have a sigma invariant set that has we have a subset of the torus that's invariant under a non-lacunary semigroup of integers, and it has zeros and accumulation point, so it's dense. Okay?
Is delta x minus x1?
No.
No.
It's the difference that because let me tell you what I'm trying to show. I should have maybe said this more clearly. I'm trying to show that the difference set contains a rational point. Contains 1 over q. Okay? In fact, I'm trying to show that that the point 1 over q is in delta. If 1 over q is in delta, it means that x1 is non-empty. If x1 is non-empty, it means that x1 is infinite. Okay? And so now, coming down to here, I've got these two things going for me again. Maybe I shouldn't put a minus sign here. I've got these two things going for me here. I know that 0 is an accumulation point of this sigma invariant set, and so the conclusion is that the difference set delta is all of R mod z. The difference set is also closed. I guess I should say that as well. The difference set is also closed, okay? Because x naught is closed. Okay? So I'll put that right here. X naught closed implies delta closed. The fact that delta itself is R mod z means that I can find a pair of points inside of x naught whose difference is 1 over q, and so it means that x1 is non-empty. Okay? So this implies that 1 over q, in particular, is an element of delta, and that implies that x1 is non-empty. Time. Have I already finished my time? Oh, no, I've got plenty of time. I have 40 seconds. That's plenty. How long is it going to take to erase the board, though? That's the real clincher. No, the proof is virtually done, because now all that I have to do, you can see how I set up this inductive type argument. Now what I want to do is I want to define a set x2. x2 is going to be defined to be the set of points inside of x1 with the property that x plus 1 over q is in x1. I'm playing exactly the same game again, because now x1 satisfies all the same hypotheses that x0 originally did. I just go through exactly the same argument, and I get a whole sequence of sets. I don't know how many sets I need. I can't figure that out in 5 seconds. So you just keep going, and you get a bunch of sets where they're nested, right? I have x0 is a superset of x1, is a superset of x2, and so on. They all satisfy all the hypotheses that I started out with, being closed, sigma invariant, and infinite. And I also know that if I start out with a point way out here, if I have a point x, which is out here, maybe I'll go ahead and give myself a little bit of room. Here's xi, and here's xi plus 1. So I'll start off with a point that's in xi plus 1. Then I know that x plus 1 over q is in xi. Then I know that x plus 2 over q is in the next set. X plus 3 over q is in the next set. Keep going all the way around, and what do you get? You get a set of points which is 1 over q dense inside of the unit interval. Okay? So the conclusion here, is that x0 is 1 over q dense. Okay? 1 over q was less than epsilon, and so we're done. x0 is a closed set which is dense in the circle, and so that implies that x0 is the whole circle. So that's the proof of Furstenberg's orbit closure theorem. It took a little longer than I thought, but it's a really beautiful proof, I think. And I tried to explain all the details, but if you have any questions, please feel free to ask me about them. I also put some exercises on the sheet to help you understand some of the little bits of the proof a little bit better. OK, thanks. I'm going to stop there.